Welcome to Introduction to Geology. I'm Dr. William Patterson. Today we will be talking about sedimentary rocks, surface processes of the rock cycle. This is part 1 of 4, in which we're going to focus on physical and chemical weathering, as well as transportation of the weathered materials. Rocks are formed by surface processes. Sediments are produced on the Earth's surface as a result of weathering. Sediments are transported, becoming sedimentary rock, after they come to rest. Sedimentary rocks provide evidence of ancient sedimentary environments where they formed. Much of the Earth's surface, including its seafloor, is covered with sediment. These layers of loose particles have diverse origins. Most sediment is created by weathering of the continental crust. Some sediment is the remains of mineral shells secreted by organisms and some organic matter, whereas others consist of inorganic crystals that precipitate when dissolved chemicals in oceans and lakes combine to form new minerals. Sedimentary rocks were once sediments, so there are records of the conditions at the Earth's surface when and where those sediments were deposited. Geologists can work backwards to infer the sources of the sediment from which the rocks were formed and the kinds of places in which the sediment was originally deposited. The top of Mount Everest, for example, is composed of fossiliferous limestone. What this means is the Coma-Langma limestone at the top of Mount Everest was once at sea level during the Ordovician about 470 million years ago. Weathering is the general process by which rocks are broken down at the Earth's surface to produce sediment. There are two types of weathering. Physical weathering takes place when solid rock is fragmented by mechanical processes, such as freezing and thawing or wedging by tree roots, that do not change its chemical composition. The rubble of broken stone that's seen at the top of mountains and hills is primarily the result of physical weathering. Alternatively, chemical weathering refers to processes by which the minerals in a rock are chemically altered or dissolved. The blurring or disappearance of lettering on old gravestones and monuments is caused primarily by chemical weathering. Erosion refers to processes that dislodge particles of rock produced by weathering and move them away from the source area. Erosion occurs most commonly when rainfall runs downhill. Transportation refers to processes by which sediment particles are moved to sink areas. Transportation occurs when water, wind, or the moving ice of glaciers transport particles to new locations downhill or downstream. Deposition, which is also known as sedimentation, refers to processes by which sediment particles settle out as water currents slow down, winds die down, or glacial edges melt to form layers of sediment in sink areas. In aquatic environments, particles settle out, chemical precipitates form and are deposited, and the bodies and shells of dead organisms are broken up and deposited. Burial occurs as layers of sediment accumulate in sink areas on top of older, previously deposited sediments, which are compacted and progressively buried deep within a sedimentary basin. These sediments will remain at depth as part of the Earth's crust until they are either uplifted again or subducted by plate tectonic processes. The asteroid at Chicxulub has entered the Cretaceous. India smashes into Asia, punching up the Tibetan Plateau 20,000 feet high. Material lifted high into the atmosphere, weathering rapidly to form massive amounts of sediment that pour into the Indian Ocean, drawing down CO2, changing atmospheric chemistry. This massive two-continent pileup is a major aspect of the long cooling trend of the Earth's atmosphere that has continued until recently when we began our experiments with the burning of fossil fuels, re-elevating the atmosphere in CO2. We'll get back to this in a later module.
The race was definitely underway. I had witnessed the start, and was sure of that much. But what now? What comes next?
Caused by pressure, heat, and chemical reactions, by which sediments buried within sedimentary basins are lithified, or converted into sedimentary rock. Lithified means to rockify, or to become rock. Weathering and erosion is the source of sediment. Chemical and physical weathering reinforce each other. Chemical weathering weakens rocks and makes them more susceptible to fragmentation. The smaller the fragments produced by physical weathering, the greater the surface area exposed to chemical weathering. Together, physical and chemical weathering of rock create both solid particles and dissolved products. Erosion carries them away. These end products can be classified either as siliciclastic sediment or chemical and biological sediment. The complexity of sedimentary processes requires us to classify sediment, to break sediment into various categories. Starting with siliciclastic sediment, here we see some volcanic sediment deposited on Deception Island in the Antarctic Peninsula. Chemical sediment seen here on the Altiplano of Bolivia is an example of an evaporite sediment, in this case a variety of salts, and biological sediment. Using my sulfur scale here in Belize, this is a coral reef. Much of the debris here you see below me is ground up coral and algae. Current strength and distance of transport are going to affect the size of clastic particles. Here we see the size ranging from gravel to sand to silt to clay. Gravel and sand are easy to see. Silt you can see if the light is just right. Clay particles you're not going to be able to see. One of the ways we differentiate between these silt and clays is by putting them in our mouths. Silt ground between your teeth will feel gritty, whereas clay will feel smooth, which is why we use it in things like milkshakes and chocolate. Sorting of clastic particles occurs during transportation. We can have materials that are consistently and therefore well sorted, or sediment that's deposited in a more vigorously changing environment that results in it being poorly sorted. Here we see as an example the sorting of rice grains. Nice clean rice here, and it's going to be a tough sell here. The rounding of clastic particles is also going to be a function of the distance of transport, with short transport resulting in angular fragments that are larger. Moderate transport is going to round the particles, making them smaller at the same time, and long transport is going to result in a well-rounded, smaller grain. The angularity is reduced simultaneously. We're going to knock the edges off of these things, particularly the corners. The little points are going to be knocked off quickly. Here we have that example from Deception Island that I showed you a few seconds ago. It's located here. This is South America, Tierra del Fuego, and the Antarctic Peninsula. So we're going to zoom into this area, and zooming in a little further, you see a little donut-shaped island here. And then from an aerial view here, it's called Deception Island because people didn't know for a while that you could actually sail a ship into this bay here inside this volcano. This is the passage through Neptune's bellows, about 90-mile-an-hour winds. So windy it blows in your nose and out your ears. And a view of the cliff. So this is the weathering volcanic material that is being converted into that sand that we see here. Skua hanging out next to an old whaling ship. Now, if you look closely here, what you see is bits of siliciclastic volcanic debris. So this is all weathered from these cliffs of this active volcano. Here we see some Gentoo penguins and some National Geographic photographers doing National Geographic photography stuff. Alternatively, we have chemical mixing vats that include oceans and lakes. The chemistry is going to be determined by the long-term weathering of the Earth's surface materials for the oceans, and in lakes, the local weathering of material. These rocks in the background here are dissolving, and those ions are entering this lake system. Ultimately, when the water molecules are removed through evaporation, the ions get closer together. More concentrated means precipitation. Physical and chemical weathering of pre-existing rocks results in clastic particles that are transported and deposited as sediment. Clastic particles range in size from boulders to particles of sand, silt, and clay. They also vary widely in shape. Natural breakage along bedding planes and fractures in the parent rock will determine the shapes of boulders, cobbles, and pebbles. Sand grains are the remnants of individual crystals formerly interlocked into parent rock. Their shapes tend to reflect the shapes of those crystals. Because most clastic particles are produced by the weathering of common rocks composed largely of silicate minerals, sediments formed from these particles are called siliciclastic sediments. The mixture of minerals in siliciclastic sediments varies. Minerals such as quartz resist weathering and thus are found chemically unaltered in siliciclastic sediments. These sediments may also contain partly altered fragments of minerals such as feldspar that are less resistant to weathering and therefore less stable. Still, other minerals in siliciclastic sediments, such as clay minerals, are newly formed by chemical weathering. Deposition starts when transportation stops. For clastic particles, gravity is the driving force of deposition. The tendency of particles to settle under the pull of gravity works against a current's ability to carry them. A particle's settling velocity is proportional to its density and its size. Because all clastic particles have roughly the same density, we use particle size as the best indicator of how quickly a particle will settle. In water, large particles settle faster than small ones. This is also true in air, but the difference is much smaller. Current strength, which is directly related to current velocity, determines the size of the particles deposited in a particular place. As a wind or water current begins to slow, it can no longer keep the largest particles suspended, and those particles will settle out. As the current slows further, smaller particles will settle. When the current stops completely, even the smallest particles will settle out. Now let's talk sedimentary basins. Sediment tends to accumulate in depressions in the Earth's crust. Depressions, in turn, are formed by subsidence. Sedimentary basins are depressions filled with thick accumulations of sediment, making them a sink for sediment. This is an example of an alluvial fan from Death Valley, California. Spring melt rushes rapidly down these slopes, depositing thick sequences or thick fans of quartz and feldspar. In British Columbia, on the west arm of Kootenay Lake, we see the formation of alluvial fans here from Mill Creek in Harrop and Kokanee Creek here that are working their way into and filling up the west arm of Kootenay Lake. Thus, water rushing down slope until it reaches the basin is slowing down and dropping its particles. In this case, some particularly large particles, or here we're looking at Kokanee Creek as it roars down the mountain, ultimately sourced from stunning Gibson Lake in Kokanee Glacier Provincial Park. Most of the large boulders are moved downslope during the spring melt runoff, just as they are in Death Valley, California. The difference being here, it's relatively humid for most of the year, with our fire season being in July and August, where we have high temperatures, drought, and wind. Now, a little closer to home, we can see a great example of, as currents slowing down, sediment dropping out. You may find dust bunnies, dirt balls, whatever you prefer to call them, accumulating under your furniture or along the walls in the kitchen because the air currents are slowest near obstructions. So just like in nature, sediment will accumulate when the current speed is reduced. Here in your house, sediment is going to accumulate where the air currents from your feet rushing around, stomping, maybe your pet's going crazy. Those air currents diminish as they approach walls and beneath furniture, and you get deposition. Sedimentary basins can be broken into a couple basic categories. Rift basins and thermal subsidence basins are tectonically driven examples. In rift basins, we have crustal stretching. The stretching of the crust results in a thinning of the crust. Ultimately, when the crust is stretched enough, you see downdrop blocks that are moving along normal faults. These downdrop blocks are then going to be covered with sediment that's derived from land adjacent to this fault system. Ultimately, sediment is going to cover this fault system completely, as it has on the east coast of North America. So this would be called a passive margin. There's no longer any tectonic activity at this margin. A third type of sedimentary basin develops at convergent plate boundaries where one plate pushes up over the other. The weight of the overriding plate causes the underlying plate to bend or flex downward. This is the flexural basin. The Mesopotamian basin in Iraq is a flexural basin formed when the Arabian plate collided with and was subducted beneath the Eurasian plate. The enormous oil reserves in Iraq, second only to Saudi Arabia's, owe their size to having the right ingredients in this important flexural basin. Essentially, oil that formed in the rocks that are now beneath the Zagros Mountains in Iran was squeezed out, forming several great pools of oil with volumes larger than 10 billion barrels. Sedimentary basins that form on rifted continental margins, again, start as a rift valley, as we've seen in the East African Rift. The downdrop crustal blocks are forming normal faults. They're going to compensate for this stretching. As this material moves away from the spreading center, it's going to cool, it's going to become more dense, and it's going to sink. It's going to form, ultimately, a depression. So the rift develops as hot mantle materials well up, and the lithosphere heats, stretches, and thins. Transportation of particles via water, glaciers, and wind are going to be the cap material here, which is the sediment, covers this normal faulted material. As seafloor spreading begins, subsidence through cooling and thickening of the lithosphere is going to occur. So this material moves away from the hot spreading center here, cools off, and in cooling it becomes more dense. Now at this point, Evaporites, deltaic sediment, and carbonates can be deposited. Sediment matters here. If there is sediment, we have deposition of deltaic sediment or perhaps evaporites. If no sediment is present, then carbonates can be deposited. Carbonate-producing organisms don't like sediment, so you won't find coral reefs near large rivers. You'll find coral reefs in locations where there's very little clastic input. The clasts plug up the filter feeders that make up much of a carbonate reef, and therefore carbonate platforms can't form where there's significant clastic input. As this thermal subsidence of the basin continues, we get what are called continental shelf deposits. This is the new continental margin and continental shelf. Again, a good example of this would be the eastern coast of North America, in particular, say, Georgia, South Carolina, North Carolina, Virginia. These deposits are then buried by accumulation of further sediment, and they may undergo diagenesis. This continental crust is going to sag from the weight of sediment and the cooling of the lithosphere, creating what's called accommodation space. This is space to accommodate sediment. Out in the center of this spreading, now widely spread rift, we have an abyssal plain, a deep water, flat surface that's covered with layers of very fine-grained sediment. The creation of abyssal plains is the result of the spreading of seafloor via plate tectonics and the melting of the lower oceanic crust. Covering over 50% of the Earth's surface, these abyssal plains form on the deep ocean floor, generally at depths of 3,000 to 6,000 meters or 10,000 to 20,000 feet. They are among the flattest, smoothest, and least explored regions on the Earth. Abyssal plains are key geologic elements of oceanic basins, along with elevated mid-ocean ridges and the flanking abyssal hills. We probably know quite a bit more about the surface of Mars than we do the abyssal plains of the Earth. Stay tuned for more information on sedimentary rocks and sedimentary environments.